Hi everyone. Before we get into our kind of post hoc test, let's take a big step back a little bit in terms of kind of how cool what we're doing is. Because I think it's sometimes when you jump right into ANOVA, you kind of lose perspective a little bit about what we're doing. So we are actually, you can kind of think of it this way. We're able now to ask a question when we're running an ANOVA. If we go back to our old hypothesis testing procedures, we are effectively setting up a problem where we're asking ourselves, our H naught that we're assuming is that our mean of 1 is going to be equal to our mean of 2, equal to our mean of 3, where 1, 2, and 3 are our 3 different treatments. Basically, it's fertilizer 1, 2, and 3. So we're able to run a test that's asking, are the means of these 3 different variables in terms of how they affect the outcome or the yield, are they the same? So this is a pretty cool, because previously we were just able to do 2 at a time, t-test or 2-test comparison. Now we can run any 1 through n variables, or actually more accurately, each of these 1, 2, 3, our k here will be equal to 3. So in this notation, our k, independent random samples, is going to be equal to 3. Our capital N, so when we actually calculate our degrees of freedom, is going to be equal to k minus 1, and it'll also be equal to our residuals, n minus k. And in this problem, or with this data set, we see that we have 96. So when we look back at our residuals, or our kind of total error, basically, when we analyze that table, you'll sometimes see residuals. You can kind of call that, like, essentially, this is effectively going to be between the treatments. You can call this this here our error or residuals. So sometimes error is going to be referred to here. So just to make sure that we're clear about that. And then you can total, essentially, each of these values together for the total value for your analysis. So this is the utility of what we're doing. So we're able to analyze basically any 1 to k system to see, are they the same or are they different? So that's a really, really cool way that you can structure how unique ANOVA is. The other thing that we want to say is the way that we set up these expressions, so the sum of squares, right? All of these values are going to be positive. So even though we've done our f-test for variances and we've set up the two-tailed test there, because of the way that we structure and calculate, because eventually f is this ratio where these are only positive values. So it'll only go from 0 to very, very large values. So when we set up this test, this is going to be yet another example, like the chi-squared goodness of fit test, where we are only going to get f values or chi values from 0 to, basically infinity. Which means that when we're doing our third test, our confidence interval, our alpha is going to be 0.05. That is why if we have an alpha that's less than 0.05, this means that we are going to reject H naught, meaning that they are statistically significant. So we can kind of see that manifest just right there. So just some background. And again, a lot of times, it's fun to kind of jump right into the analysis for ANOVA and the ANOVA tables, but it's always nice to also take a step back and make sure that we understand the context of basically what we're learning. So hope that's helpful, and we'll see you then. Thanks.